If you're new here, don't forget to hit that subscribe button and ring the bell for notifications. Today, we're diving deep into one of the most fascinating topics in physics and medical imaging: energy spectrum and characteristic radiation. This topic is crucial for understanding how X-rays are produced and how they're used in medicine, industry, and research. So let's jump right in. Slide 2. What are X-rays? Let's start with the basics. What exactly are X-rays? X-rays are invisible electromagnetic radiations. You can't see them, but they carry very high energy. They travel at the speed of light. That's about 3 times 10 to the power 10 centimeters per second. Unlike visible light, X-rays cannot be focused by lenses because of their extremely short wavelength. They are neutral. They are not deflected by electric or magnetic fields. They're also highly penetrating, which is why they can pass through soft tissues but are absorbed by dense materials like bones. Their energy range extends from a few kilo-electron volts up to several mega-electron volts, covering a wide portion of the electromagnetic spectrum. Slide 3. Production of X-rays. Now, how are X-rays actually produced? When high-energy electrons strike the target material inside an X-ray tube, something interesting happens. A fast-moving electron collides with an atom and knocks out an inner shell electron, usually from the K shell. This creates a vacancy in that shell. An electron from an outer shell, such as the L or M shell, then drops down to fill that vacancy. When it does, it releases energy in the form of an X-ray photon. This process is called characteristic radiation because the energy of these emitted X-rays depends on the target element being used. Slide 4. Characteristic radiation. Characteristic radiation consists of X-ray photons with specific discrete energies produced when an outer shell electron fills an inner shell vacancy. Each element produces its own unique set of characteristic X-rays. For example, tungsten produces tungsten characteristic lines, while copper produces copper lines. On the spectrum, these appear as sharp peaks superimposed on the continuous background. There are different types of characteristic X-rays. K-alpha radiation occurs when an electron drops from the L shell to the K shell. K-beta occurs when the electron falls from the M shell to the K shell. L-series radiation occurs when the vacancy is in the L shell. These transitions give rise to distinct energy lines unique to each target material. Slide 5, energy spectrum. Now let's look at what an actual X-ray energy spectrum looks like. On the horizontal axis, we have energy in kilo-electron volts, and on the vertical axis, intensity of X-ray photons. There are 2 main components. First, the continuous curve, known as the Bremsstrahlung spectrum or braking radiation. This occurs when high-speed electrons are slowed down by the target material, producing X-rays of varying energies. Second, the sharp peaks on the curve. These are the characteristic X-rays. The taller peak usually represents K-alpha, and the shorter one represents K-beta. So every X-ray tube emits both continuous radiation and characteristic peaks simultaneously, creating the complete X-ray energy spectrum. Let's take tungsten as an example. It's the most common target material in X-ray tubes. In a 70 kilovolt peak X-ray tube, tungsten produces K-alpha radiation at about 70 keVs, K-beta radiation at about 80 keV. Characteristic X-rays make up about 28% of the total output, while the rest is continuous radiation. Tungsten is used because it has a high atomic number, Z equals 74, which makes it very efficient at producing X-rays. The energy of characteristic X-rays can be estimated using the equation E equals 13.6 Z squared, 1n1n2 squared. This shows that as the atomic number increases, the characteristic X-ray energy increases dramatically. Slide 7, factors affecting the spectrum. There are 3 main factors that affect the shape and intensity of the X-ray spectrum. First, tube voltage, kVp. When we increase the tube voltage, the maximum energy of the X-rays increases, the spectrum shifts to higher energy, and the overall intensity rises. Second, target material. Different target elements produce different characteristic peaks because each has a unique atomic number. Higher atomic number materials are more efficient and produce higher energy X-rays. Third, tube current math. This only affects the overall intensity. Increasing the current increases the number of photons, but does not change their energies. So, if you need more X-rays without changing their energy, increase the current. Slide applications. Now, where do we use X-rays? In medicine, diagnostic imaging such as regular X-rays, radiation therapy for cancer treatment, CT scans for 3D imaging of the body. In industry, material inspection and non-destructive testing, quality control for detecting defects in machinery and components, security scanning systems at airports. In research, X-ray crystallography to determine molecular structures, spectroscopy and fluorescence analysis for studying materials. From hospitals to research labs and industries, X-rays are used everywhere. Slide 9, Key Properties Summary. Let's summarize the key properties of X-rays. They are invisible electromagnetic waves. They travel at the speed of light. They are highly penetrating and can pass through most materials. They ionize atoms and molecules. They affect photographic film and cause fluorescence in certain crystals. They produce chemical and biological changes. Their intensity decreases with distance, following the inverse square law. And they have both continuous and characteristic components in their spectrum. Slide 10. Thank you. And that brings us to the end of this session on energy spectrum and characteristic radiation. Today we learned about the nature and properties of X-rays, how characteristic radiation is produced, the structure of the X-ray energy spectrum, the main factors that influence it, and the various applications in medicine, industry, and research. If you found this tutorial helpful, give this video a thumbs up, leave your questions in the comments, and don't forget to subscribe for more tutorials on radiography and physics. Thanks for watching, keep learning, stay curious, and see you in the next one.